The mean value theorem. The mean value theorem is one of the most important theorems in calculus. But before presenting a formal definition and explanation of the same, I would like to show you the mean value theorem in action while driving a car. It will help you assimilate what the mean value theorem is all about. So, for the next 46 seconds or so, you will be seeing the video of speedometer of a car which I made while I was driving the car. Please pay attention to the movement of the needle of the speedometer, which tells you the instantaneous speeds of the car at different instants. Towards the end of the short trip, we will calculate the average speed of the car and connect it backwards or compare it to the observations about instantaneous speeds of the car. No, I drove a real car. Here we go. Okay, so let us now calculate the average speed of the car during the short trip. The average speed is given by total distance traveled upon the total time taken. The total distance traveled by the car during the short trip was 0.3 kilometers. How did I get to know this? You must have observed towards the beginning of the trip I had set the reading of the odometer to 0, and when the trip ended it reads 0.3 kilometers. That's how I get to know the total distance as 0.3 kilometers. The total time of the short trip was 45 seconds. Now how do I get to know this? You can rewind the video and check for how long does the speedometer video lasts. So that's how I get to know the total time taken was about 45 seconds. Now if you plug in these values into the formula and use appropriate unit conversion, you will get to know that the average speed of the car during this short trip was 24 kilometers per hour. Okay, now my question is, did the car ever attain the speed of 24 kilometers per hour during the trip? I mean, was the instantaneous speed of the car ever equal to 24 kilometers per hour? Yes, it was. In fact, it happened twice that the instantaneous speed of the car was equal to 24 kilometers per hour. When all did this happen? If you rewind the video, you'll see that the instantaneous speed of 24 kilometers per hour was attained for the first time during acceleration and for the second time during deceleration. Now, was this a coincidence that the average speed of the car did match the instantaneous speed of the car, and that too twice? No, this was not a coincidence. In fact, this is what the outcome of the mean value theorem is. As per the mean value theorem, the average speed of the car had to match the instantaneous speed of the car at least once. Now, let us take a look at the formal definition of the mean value theorem and connect it mathematically to our observations. Here is the formal mathematical statement of the mean value theorem. It says that for a function f, which is a function of x, if it has these two traits, Number one, it is continuous over a closed interval, say a comma b, and second, it is differentiable over the interior of the same interval. Then, as per the mean value theorem, there would be at least one value of x in the interior of the interval a comma b. Let's call this value c, such that the derivative of the function at that particular value of x, f dash c, would be equal to the number fb minus fa upon b minus a. What does this mean? There are two ways to understand this theorem further. First, graphically, and second, in terms of average rates and instantaneous rates. So let us first take a look at the graphical aspect of understanding the mean value theorem. Here in this diagram, I have shown a smooth, continuous, differentiable curve over the closed interval a comma b. As per the mean value theorem, graphically, the slope of the secant line connecting the points a comma fa and b comma fb, which is given by fb minus fa upon b minus a, would be equal to the slope of tangents to the graph of the function at different instants, which is given by the derivative value. So we can see that in this graph, the slope of the secant line does match the slope of tangents drawn to the graph at 4 different instants. This is one x value, this is another x value, this is another x value, and this is yet another x value. The slopes of these 4 tangent lines are each equal to the slope of this secant line because all of these lines are parallel to one another. The second aspect of understanding the mean value theorem is in terms of the average rates and instantaneous rates. If you look the right hand side of this expression carefully, you will realize that all that is written here is average rate of change of the function fx over the interval a comma b, which is given by the change in output fb minus fa over the change in input b minus a, equals the instantaneous rate of change of function at different instants over the interval a comma b. We know that the instantaneous rate of change is given by the derivative. How does all of this relate to the car driving experiment? I drove the car on a straight road, and let us now attach some mathematical symbols and notations to our experiment. Let's say the position of the car at any instant t is given by the position function s, which is a function of t. The position is read in kilometers and time t is measured in seconds. We can see that the position function, or I should say, it is safe to assume that the position function of the car across the time interval 0,45 across which the journey lasted is continuous, because the car would not have jumped from one position to another position. It would have attained all the positions in between, and it is differentiable because at any given instant it will be having a well-defined velocity or speed. So the position function s, the time t, this function is differentiable and continuous within this interval. These are the statistics. Initially at t is equals to 0, my position was at 0 kilometers, and towards the end of the trip, after 45 seconds, my position was at 0.3 kilometers. Let us compute the average rate of change of the position function over this time interval. Average rate of change of the function s over the interval 0,45 is given by s45 minus s0 by 45 minus 0, same as fb minus fa upon b minus a. Plugging in the values and using appropriate unit conversions, we see that this comes out to be 24 kilometers per hour. We can interpret average rate of change of position as average velocity over this interval, and further, because the car was traveling on a straight road, we can call the average velocity as the average speed. So we have just found again that the average speed of the car over this time interval was 24 kilometers per hour, and we had already seen that the instantaneous speed of the car, which can also be interpreted as the instantaneous rate of change of the position, which means the instantaneous velocity, which in turn means the instantaneous speed, was equals to the average speed at two different instants.